Time for questions. You can come to the mic, or you can post questions in the Swapcard app. So before you come, I will start with some questions to the speakers. First and foremost, thank you so much. So we had a very diverse view, one on the data centers, AI factories, CFDs, advanced foundation models, AI agents, looking at new algorithms that are going to accelerate AI for science and AI in general, HPC, thinking about various reduced precision and mixed precision type methodologies, which are super impactful, and AI for science, how to bring more physics-informed methods that are very unique for scientific machine learning models. So first of all, yeah, thank you so much for providing your insights and really, really great presentations. I think we already have a question there, so please go ahead.
Yes, hello. My name is Edgar. I'm from Riga Technical University. And I wanted to ask a question. As we get better and better simulations using AI, are we getting better and better experiments that validate these simulations? When thinking about AI-guided science discoveries, are scientists utilizing AI in the right way? Do we need really these large models, or maybe we could, with what we already have, do more?
Yeah, I think it's a good question, and depends very much on the context. There are certain problems where scientific simulators are accurate and cheap. And when you have that kind of situation, coupling it with an AI system can be really amazing, right? So there are people who are designing experiments for, I think you were there at the meeting last week, for quantum entanglement, completely based on AI, right? So what can these methods do that standard optimizers cannot? You have a problem where topologies change, right? How many mirrors do I put? And then you have problems where you have discrete parameters, integer parameters, continuous parameters. Some of these models, if we have good, cheap simulators, they're able to do incredibly good reasoning, right? So short answer to your question is, when the simulator, whether it's an AI surrogate or a physics simulator, is accurate, and when you couple that with AI systems, then you have opportunity to do incredible things. But in many cases, that is not the case in many problems. AI surrogates are not accurate enough, and physics solvers are rich, but they're expensive. So there, I feel there's still a very long way to go for AI to have an impact. So it depends on the context.
Okay. Please.
Yeah, well, the tendency I think we're seeing is that, well, there's multiple combinations. Well, firstly, in terms of whether you have surrogates or you have a physics-based simulation, then there are lots of techniques to combine the two. For example, you may have AI-driven preconditioners to do much better preconditioning as opposed to being human-guided preconditioners on some black art, and these will significantly accelerate the simulation itself. And typically these surrogates or physics for neural networks or any of these assistive AIs are fairly lightweight compared to the simulation itself. But then it still will significantly accelerate the simulation itself. But the real deal is when these will be combined in the entire scientific process of hypothesis generation, and then planning experimentation and conducting the experiments or the simulations or whatever itself, and doing the analysis. There's a paper, AI Scientist by Sakana AI. I don't know, you may know it. And that's one exemplar. And although the domain was limited, in principle, I think a lot of people feel that's the way the science is going, that the entire scientific process will be driven by essentially augmenting or replacing the human elements with respect to these generation. And there are more systems I can't speak about, actually, that are pretty amazing in this respect, that would go even beyond what the AI scientist paper did. So, but then that will take significant amount of compute, because the scientific process is also involves resource. Any scientific process involves tremendous resource. And if we have intelligent AI that allows to generate multiple zillions of hypotheses, you can't run all the experiments, right? Because they're too expensive. So you need a process of, for example, paring down. But how do you pare down? Right? In the human process, it's like grants or by human intuition. So you need to bring those into the process. So by speeding things up, we may accelerate science, but the overall demand for compute will skyrocket. Not just because of the AI itself, but the process itself will accelerate much faster, requiring more resource, be it AI or more importantly, the experiment itself.
Thank you.
To add some perspective from the experimental science point of view, so one of the desires is basically, so beam time is quite expensive, and literally people wait about a year to get a beam time of 8 hours. So one of the ideas is around, can we actually simulate what the sort of a data I'm going to get at it. So although we could do atomistic simulations, in terms of experimental data, we are not there yet. The gap is quite large. The experimental data is sort of totally different in terms of characteristics, but we actually get it from the simulation. It's representative, but not quite. The gap is quite large. So that's one of the active areas they're trying to kind of bridge it to see whether, and this is where the generative models are not quite there yet either, partly because generative models are nice, you could generate an image, someone looking at the beach, but you don't really care which direction. But on the scientific front of it, it has to be scientifically grounded. So bringing that scientific grounding is much of a challenge on it, and that's an active area of research, just to mention it.
Okay. Questions? I have a...
Oh.
Yeah. Oh, please.
Yep. Hi, Andrew Shao. I'm a senior HPC and AI research scientist at Hewlett-Packard Labs. One of the questions, this is going to be a little bit more of a specific one, in terms of the convergence and divergence of HPC and AI, one of the things that we see in AI, right, is that it's very high arithmetic density, right? Whereas a lot, even in comparison to traditional simulations, very low arithmetic intensity. So I'm kind of curious to know your opinions on how we can increase the arithmetic intensity of our traditional simulations, whether it's by something like FP64 emulation, whether it's by increasingly high orders of numerical schemes, or other kind of techniques that you've thought about or are considering.
Oh, is it me? Okay. Yeah. Well, firstly, as we move from training-oriented AI, which had been the case for the past, 2 or 3 years ago, but now we're progressing towards increasingly inference-based, inference-oriented AI, and of course, infrastructure supported. And the reason, and there are multiple reasons why. Obviously, as AI has become more commercially viable, the users of the AI will become more predominant, and thus AI. And then this is now aggravated by this extensive movement toward reasoning models, in which you've got to do tons of inferences in order to just generate one token. So, and the inferences, and these low latency inferences, if you do the right, you do these right architecting and modeling analysis, becomes very much dominant more on memory bandwidth rather than compute. Because in inference, you can use much lower precision compared to training. But you still can't escape from the fact that when the transformers work, you have the prefill and the attention layer, and then you have the whole fully connected layer. And the fully connected layer is very much memory bound, because basically it's L2 loss. So, but going like 4 bits, the compute shrinks, and also it shrinks because you go to things like MOEs, because they have smaller models, but still the memory bandwidth is there because you need to have very low latency, high turnaround. So the tendency has been for the AI architecture to increase bandwidth. So there, it sort of matches some of the tendency towards HPC. But you're right in saying that but on the HPC side, can it increase the computational efficiency more? Well, we can, so that's what I hinted by going to lower precision, being able to, we can utilize the bandwidth more. That's, I think, will be the tendency. Of course, we can go to other things like high order methods as well. That's another thing I didn't hit, but that's what some people are doing. And high order methods don't require that much precision, but still you can make it computationally intensive. So, there's a whole movement, not just with dense linear algebra, but in sparse methods, how to go to lower precision to essentially try to save on the data movement while in data movement in order to increase your application performance. And there are lots of tricks, numerical tricks, and more fundamental numerical methods, I think, will come forth in the next several years to try and to accelerate and make use of these low precision techniques. Yeah.
Thank you.
Okay, so we are slightly running out of time, although we started a little late. So in the interest of time, I'm going to ask you one question, and I want a number in terms of years. It's a prediction. Okay, so we talked about AI for accelerating science and AI implementations and infrastructure for AI, ModSim, and other things. So, and also there is this promising avenue of accelerating ModSim using AI, and the numbers are anywhere between 10x to 100x, even 1000x, right? The weather prediction model that you showed compared to the numerical weather prediction model versus surrogate model. There's a lot of success in weather, right? So if we have to take that and say, more, I wouldn't say more challenging, but other science problems, let's say turbulence or DFT and other kinds of problems, pick any application and say, how many years we need to reach to the point where we say, okay, thanks to AI surrogate models, we have accelerated simulation by 100x. I want 100x. How many years we need to wait?
My feeling right now is that we're still a bit early, so I would
number.
Go
I want a number.
Okay. 10-ish.
10?
5 to 10.
Okay.
5 to 10.
On my optimistic day, 100 years.
Wow, okay.
Because you said all problems. You didn't say
let's say
problems.
killer, one killer app.
Oh, one killer app is already there.
It's already there.
Yeah.
It's already there. Well, I'm saying less than 5 because that's our timeline for next machine.
Yeah.
And
I would go less than 5 as well. I think specifically if you ground a particular problem with the rate of advances we make and with the arrival of next machines. So.
All right. So 5, less than 5. Great.
Let's see.
Okay, with that, thank you all. A round of applause to the speakers. Again, thank you. And thank you all for participating.